Welcome all of you. Today we are going to discuss the concepts of divergence and curl. In second unit magnetostatics we are having a concept called as curl. To understand that concept of curl, first we need to know how we got the divergence concept in first unit. For that, let us see a small derivation where we are going to apply Gauss law to a small differential volume element. That means if we consider Cartesian coordinate system, that means x, y, z Cartesian coordinate system, and if I consider a point P in that system, wherever we are considering that surface is called as Gaussian surface, because we already defined that the surface on which we are applying the Gauss law is called as Gaussian surface. In that Gaussian surface I am considering a point P. In that complete Gaussian surface, instead of taking the complete surface, I am taking only a small differential rectangular volume of the surface. Okay, this is the small differential volume of the Gaussian surface that you are considering, whose length, breadth and width are delta x, delta y and delta z. These are the dimensions of this small differential volume. Now I am considering the same point P exactly at the center of this small differential Gaussian surface. Okay, so this P is exactly at the center of this differential volume, so that from wherever you look, that length from that point P will be some delta x by 2, delta y by 2, like that we can write. This is exactly at the center of this cube, rectangular cuboid. Okay, now we are applying Gauss law for this differential volume of the element. Generally, if we consider a point P and if we consider electric flux density d bar, the electric flux density d bar at this point P is generally given in Cartesian system as dx ax bar plus dy ay bar plus dz az bar. That means we are splitting the function to x component, y component and z component. Now, as we are considering only a small differential volume, in that volume you are taking the flux density, electric flux density as d naught. Let it be some d naught. Now your d naught is the electric flux density at this point P, which is present in the differential volume of this element. Okay, so here we can write it as dx naught ax, dy naught ay plus dz naught az. That means this d is the complete electric flux density at a point P for the complete Gaussian surface, but this d naught is the electric flux density at this point P only in this differential volume of the element. That is the difference between these two. Okay, now what is the integral form of Gauss law? Gauss law states that the electric flux coming out of a closed surface is equal to the total charge that is present in the closed surface. In integral form, it can be written as q equal to closed surface integral of d bar dot ds bar. Okay, d bar dot ds bar. This is the integral form of Gauss law, which states that charge q is equal to closed surface integral of d bar dot ds bar. Okay, so you can apply this equation for this differential volume of the element. While applying this equation, we are saying that complete surface integral of d bar dot ds bar is to be done on this complete surface of the differential volume that you are considering. Here, for this complete volume of the element, how many sides or surfaces we can observe? We can observe from front side, we can observe from back side, from left side, from right side, from top and from the bottom. Okay, so we can split the surface integral to 6 parts. That means q is equal to integral front side plus integral back side plus integral left side plus integral right side plus integral top plus integral bottom. If we calculate the integrations for all these surfaces, from whichever side you are looking, from that side if you calculate the closed surface integral of which quantity? we are calculating this closed surface integral for d bar dot ds bar. Okay, d bar dot ds bar. All these integrals should be calculated for the quantity d bar dot ds bar. Okay. Again I am mentioning this closed surface integral can be expanded as 6 sides surface integral because we can observe this volume from 6 sides. One is from front, one is from back, one is from left, one side is from right side, one is from top and the other is from bottom. So for this closed surface, for this differential volume, we are integrating for the surface from all the 6 sides. This integral is to be applied for which quantity? D bar dot ds bar. If we calculate each integral of d bar dot ds bar separately and if we add them, then we can get the total charge Q for a differential volume of the element by using Gauss law. Okay, let us calculate the first two integrations and similarly you can apply those formulas to the remaining integrations also. So while calculating the first two integrations, consider front integral of d bar dot ds bar. How this can be calculated? If you are looking from front side, what is d bar? If you are looking from front side, front means you are observing this cuboidal structure like this. If you are observing like this, on which side you are getting? From x side you are observing. So x side dx front into, that means vectorial form of d bar is equal to its magnitude into what is the unit vector in this direction? The unit vector in this direction is ax because here d bar is acting like this perpendicular to the front side. That means your d bar will be like this perpendicular to the front side. Always d bar will be perpendicular to the Gaussian surface that you are taking according to our assumption in our previous classes. So d bar is matching with x direction, so the unit vector in this direction is ax bar. Okay, now what is ds bar? Differential surface area. Differential surface area when you are looking from x side is equal to, leave that x side and remaining sides you write delta y delta z into what is the unit vector in this direction? Again ax. Okay. Now if you calculate d bar dot ds bar, if you calculate d bar dot ds bar for these assumptions, then d bar dot ds bar means dx front. That means you are observing the d from front side of this cuboidal structure or differential volume. Okay, so dx front ax bar dot, what is ds bar here? Delta y delta z ax bar. Already we know that the dot product of two similar vectors ax bar dot ax bar is equal to 1. So ax bar dot ax bar is equal to 1. So if you apply that here, you will get d bar dot ds bar is equal to dx front into delta y delta z. Okay, so dx front into delta y delta z. If you calculate d bar dot ds bar when you are looking from front side of this differential volume. Okay, now you have calculated the value of d bar dot ds bar from front side, which is equal to dx front into delta y delta z. Now we need to calculate the magnitude of this dx when you are looking from front side. Magnitude of dx when you are looking from front side can be taken as your initial value of the dx for this differential volume. Already from our previous equation, the initial value of the d from x side when considered for this differential volume is dx naught, I have written in the previous equation, plus the rate of change of the dx with respect to x. Rate of change of dx with respect to x means dou dx by dou x. That means your dx is varying. This differential volume will shrink to 0 after some time. It will not stay constant. It will shrink to 0. Okay. As it is sinking to 0, the rate at which the differential volume is sinking is given by dou dx by dou x. In which direction it is sinking now? X direction. Into what is the distance of the point? The distance of the point from your considered direction. See, in this point is exactly at the center of this differential volume. In x side, from the starting point to this center point, what is the distance? Complete distance is delta x. Up to half of its distance is delta x by 2. Delta x by 2. This is the complete formula for D when you are looking from x side, that too from front side. Okay, your front side is matching with x direction. That should be written as initial value of the D when you are looking from x side for a differential volume element dx naught plus the rate at which the dx is changing with respect to x axis into the distance of the point P from the front side. Distance of the point P from the front side is exactly half of this delta x. So it is taken as delta x by 2. Okay. So now substitute this here. Substitute this dx front here, so that you will get the complete integral only on front side. Front side integral of d bar dot ds bar is equal to front side integral of d bar dot ds bar is equal to, substitute this value here, dx naught plus dou dx by dou x delta x by 2 into what is there here? Into delta y, delta z is there. So into delta y, delta z. So this is the formula for front side integral of d bar dot ds bar for this differential volume element. Okay. Similarly, we can calculate d bar dot ds bar for back side also. Let us do that. So now let us calculate d bar dot ds bar for back side. If you are calculating that for back side means where you can observe this is the front side. If you observe this volume from back means that back side will appear, okay, which will be again towards x axis only. So that is equal to, see, if you are considering from front side, d bar will be towards me. D bar will be towards me. If you are looking from back side, d bar will be towards that side. Whichever surface you are considering, d bar should be always perpendicular to the surface. If you are looking from front side, that means if you are observing this side, d bar will be perpendicular like this. If you are looking from back side, if I observe that back side, then you can see that back surface here, and d bar will be perpendicular to that back side. That means if this is ax bar towards front side, then back side means you should get minus ax bar. Okay, so if you observe back integral of d bar dot ds bar, then what is d bar? Dx of back side dx into, here the unit vector is minus ax. How it got, I already explained you just now. So instead of taking plus ax, you take minus ax, because for every surface d bar is always perpendicular. Front side means this is perpendicular towards plus x. Back side means that back surface will be like this, and d bar will be perpendicular towards opposite side. So front side if you are taking plus ax, back side you should take minus ax. Okay, this is the value. Next, for differential surface when looking from back side, both front and back are same dimension surfaces. So again surface area for that back side is also delta y delta z into ax. Now let us calculate d bar dot ds bar for back side. Back side means dx of back, and what is the unit vector there? We are having minus ax. Okay, Here we have written minus ax and ds bar is same. So again ax bar dot ax bar is equal to 1. So what is left out? So d bar dot ds bar for back side is equal to dx back. So d bar dot ds bar for back side surface is equal to minus of, because here minus is there, no? So minus dx back into ds formula is same, delta y delta z, that will be same, and ax bar dot ax bar is equal to 1. So if you calculate d bar dot ds bar for back side, what is the final formula? Minus dx of back side expression into delta y delta z, and if you calculate that, it will be equal to, you observe, if you are doing from back side, this dx, rate of change of dx will be negative, because if you are looking from front side, d bar will be varying towards the positive x direction. If you are looking from back side, that back surface, if it is like this, means d bar will be varying in opposite direction. That means previously if you have kept me plus, means now you should keep minus sign for back side surface. So keep minus here. So if you are applying minus, it will become dx naught minus dou dx by dou x into delta x by 2, because as both the surfaces are on same axis, formula will be same. Just the rate of change of dx will be positive from front side and negative from back side. Okay. So now what is the integral of d bar dot ds bar from back side? Integral d bar dot ds bar for the back side surface of this differential volume is, that is equal to, already we are having minus of dx of back side into delta y delta z. That means outside we should keep minus sign, because here minus is there. Minus of dx naught, here minus sign is there, dou dx by dou x, delta x by 2 into delta y delta z. Now the back side integral of d bar dot ds bar is equal to minus dx naught plus dou dx by dou x, okay, into delta x by 2 into delta y delta z. This is the formula for d bar dot ds bar for this differential volume when you are observing from the back side surface. Okay, so already we got the integration from front side as d bar dot ds bar is equal to, previously we got dx naught plus dou dx by dou x into delta x by 2 into delta y delta z. Now from our previous assumption, we should take the sum of all the integrals from front, from back, from right side, left side, top, bottom, all of them we should add now, that we have written in the previous expression. So q equal to integral d bar dot ds bar, that integral is split as 6 surfaces. Among that we have obtained 2 surfaces values. Now if I add both of these, that means front integral plus back integral is equal to, what is the front integral value? Dx naught plus dou dx by dou x into delta x by 2 into delta y delta z, plus back integral value is minus dx naught plus dou dx by dou x into delta x by 2 into delta y delta z. Now if you take delta y and delta z as common from both of them, we can cancel plus dx naught and minus dx naught. Okay. Now what is the complete value of front integral? Complete value of front integral plus back integral, that is equal to See, add both of these, you will get 2 times dou dx because both are same terms. If you are adding same terms, x plus x means 2x. So 2 dou dx by dou x, 2 dou dx by dou x into delta x by 2 into delta y delta z. So here 2 will be cancelled and your final expression for front integral and back integral surface is equal to, let us write those again. So front integral plus back integral for this differential volume is equal to, dou dx by dou x into delta x, delta y and delta z. We already know that volume of a cube is LBH, that means delta x, delta y, delta z are LBH, that is nothing but volume only. If you are applying differential values, that will become differential volume. So front integral plus back integral is equal to dou dx by dou x into delta v, that's all. Similarly, if you calculate left side integral plus right side integral, left side means from this side will come, right side means from this side. You can observe this surface. They are on which axis? They are on y axis. So your final formula will be simply dou dy by dou y into delta v. Similar to this. Similarly, if you observe top and bottom, top surface will match with z axis and bottom surface will also match with z axis. So integral top plus integral bottom will be equal to top plus bottom, they will be matching with z axis. That's why we can finally write it as dou dz by dou z into delta v. So total 6 integrals are completed: front, back, left, right, top, bottom. Front side of this surface, back side, left side, right side, top, bottom. Okay, if you add all those, then we can get the final Gauss law formula. Let us simplify that. So we know that charge q is equal to closed surface integral of d bar dot ds bar. Already we have calculated 3 sum of integrals. If you add those here, finally you will get dou dx by dou x plus dou dy by dou y plus dou dz by dou z into, among all these which term is constant, that is delta v. Okay, now you can write it as integral d bar dot ds bar divided by, if you send this delta v this side, it will become by delta v, that is equal to dou dx by dou x plus dou dy by dou y plus dou dz by dou z, which is also equal to q by delta v. As I have already explained in the previous classes, this particular term is called as divergence. Divergence of the vector d. Okay, what is d here? D is the electric flux density at this point P, which I have already marked. Okay, the divergence of any vector d is given as dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Okay, that is the concept of divergence.